Okay. Well, there's actually a committee meeting that I'm supposed to be part of, but I'm in class, so I can't go. Oh, boo-hoo.
That's really sad.
Yeah, so definitely would not want to be there.
Same committee stuff.
Yeah. Okay, now, really all I want to accomplish today is finish off what I had last time. So just a quick recap of where we're at. So systems. Of linear ODEs. So the first case that I've done, which I guess would have been closer to 2 weeks ago, is, so either way we're concerned with y prime is equal to a matrix, y is a vector, so y prime is equal to ay plus b of t. And in the case of A being diagonalizable, actually what I'll do is I'll remove this source term for the time being, just to simplify things, then I'll deal with it afterwards. So A is diagonalizable. What we found is that the solution is e to the at times a vector of initial values, where e to the at can be defined in terms of a Taylor series. Okay, the familiar Maclaurin series for the exponential. But what I have looked into since then is, what if A is not diagonalizable? So as far as where we on top of that, then we have that A is expressed using the Jordan canonical form, where J is not diagonal necessarily, but block diagonal. And then what we found, just by working with a specific example, is so using the Jordan form, we get a new system of ODEs. W prime is equal to JW. So system of ODEs of the same form, just with a simpler matrix, where W is equal to X inverse Y. All right. So what we saw there was it was not possible to separate the ODEs for W completely. They could not be solved independently of one another. Certain ones can, but not all of them. So corresponding to the cases where the Jordan blocks are not one by one. So so back to the specific example. J turned out was like lambda 1, lambda 2, and then a 3 by 3 Jordan block after these two that are 1 by 1s. Okay. Now, when we solve the ODE system of ODEs involving J, for W1 and W2, where we have these 1 by 1 Jordan blocks, we've got the same old exponential, e to the lambda 1t, e to the lambda 2t. Now, well, the solution we got here is that the unknowns W3, W4, W5 turn out to be similar, and then you do have an exponential of lambda 3 on a diagonal. But you have additional terms. Okay, so I should say this is, sorry, should be W3, W4, W5 of T. Is equal to this matrix times the initial values of W3, W4, and W5. So the additional entries that I had here were T e to the lambda 3T here and here. And then I have 1/2 T squared e to the lambda 3T. Okay. All right. So the question is, how does this matrix relate to this one? Well, for one thing, both matrices are upper triangular. And if you have a matrix that is upper triangular, then anytime you add matrices that are upper triangular, or multiply matrices that are upper triangular, the result is still upper triangular. So is this matrix obtained by like multiplying matrices like this together or adding together, that would produce an upper triangular result. But notice also what we have here is, if you look at what's multiplying the exponential, so this matrix is also equal to e to the lambda 3t. I'll just factor that out. And we get those zeros down below the diagonal, ones on the diagonal. The diagonal above, we have t. And then this one spot here, we have 1/2 t squared. Now those terms, 1/2 t squared, sorry, let me back up. 1t, 1/2 t squared. Where do we recognize those from?
Just like on.
Yeah, but those coefficients, like.
Oh, like the
Taylor's series of what?
Taylor series. Sorry, I'm just thinking about generic Taylor series.
All right.
Taylor series.
Yeah, these are the first three terms of a particular Taylor series.
Okay.
Anyone from a virtual peanut gallery? What?
It's not Maclaurin. Right?
It actually is a Maclaurin series because it is a Taylor series centered at 0.
I think I'm only thinking about that because we talked about it recently, so I'm like, no way, it could be that for other class. But, okay, I got you. Yeah, because don't we use it? Isn't that? I think it's part of your Class 16 homework too.
Yeah, the Maclaurin series of what function? A specific function.
Oh, okay.
The exponential.
Oh, okay.
Yeah, so e to the t
Yeah.
is equal to 1 plus t plus
Oh, okay.
1/2 t squared and so on.
Oh, okay.
So this is definitely related to the exponential involving something times t.
Right.
So now we know what the matrix exponential looks like for a diagonal matrix, because all you're doing is you're taking the exponential of the diagonal entries.
Mm-hmm.
But this matrix is not diagonal, so it's not at all obvious what the exponential of this matrix would be. But it would be really convenient if it would be this. Because then we can just say it's the matrix exponential always, whether A is diagonalizable or not. So what we need to do is, let's go ahead and work out the exponential of this matrix and see if this is what we get. Okay. That's going to be a pain because you have to take that matrix, raise it to certain powers. And when it's not a diagonal matrix, you're doing the matrix multiplication.
Like power method-y type stuff?
Not
really.
Well, you are taking powers of a matrix. But the problem is, we need a formula for powers of this matrix.
Okay, so it's not going to be from like multiplying it to itself.
Well, yeah, it is, but then we're going to add those, multiply by coefficients and add them together.
Okay.
Yeah, so there's more to it than that. Yeah, the power method, you're taking a matrix and you multiply repeatedly, that's a monomial. But here we're going to have a polynomial.
Okay.
Okay, so let's use this definition of the exponential, matrix exponential, and apply it to this and see what we get. Actually, you know what? No, I'm not going to do that because I already thought about that last time and it would be too difficult. I'll use something a little different. So I could use this definition of EGAT, where it's a Maclaurin series. Or I can use a different center besides 0. That's still a Taylor series. So I could do, okay. So now okay, so 18 minus, all right, actually, I'm gonna have to write this differently. All right, so e to the t is we're going to scale instead of a matrix. This is a Maclaurin series, t to the k over k factorial. But I can also write it as I take the derivatives of e to the t, but derivative of e to the t is just e to the t. So I can do that. That's just a Taylor series with a different center. The question is, what center should I choose? So I want the exponential of this matrix as lambda 3 down the diagonal times t. So you can think of this argument as playing a role of t in here. That's what I want the exponential of. So what I need to do is subtract something off from it, and that will be my center. So, so what I could do is, okay. Now, actually, this is J3, capital J3. That's my Jordan block. So, I could write it as a sum, 0 to infinity, of, so for my center, I'm going to use lambda 3 times t. So that'll play the role of t naught. And then what I'll have is J3t is what I'm taking exponential of, minus lambda 3 times t, all raised to the k power. Okay. Now, actually, I can simplify that a little bit. e to the lambda 3t, t to the k over k factorial. So I'm factoring the t to the k out of that. And then I have j3 minus lambda 3 identity. I should have an identity here also, raised to the k power. So this is how I can express this exponential. All right, so this is e to the j3t. All right. So questions about where that came from before I actually try to figure it out?
Sorry, I'm just behind writing.
Okay.
So you said E, okay, and that is J3T. Oh, okay. So you just simplified that T.
Yeah.
J3T, and then where did the T go with the other J3?
So I factored a t out of this.
Oh, okay.
But it's being raised to the k power, so that gives me a t to the k.
Oh, wait, you said you factored a T out, and then what?
But everything in here is being raised to the k power.
Right.
So the t I'm factoring out is raised to the k power. And that
Oh.
goes here.
Okay.
Yeah.
I got it.
Okay. But also, e to the lambda 3t, that factor actually can be pulled out of the sum. It doesn't depend on k. And notice that in the matrix that we got when we solved the ODEs, it had a factor of e to the lambda 3t in every entry.
Right.
So this suggests we're on the right track. Okay. So instead of just raising the matrix, the whole matrix to the k power, I'm raising this to the k power. So now j minus lambda 3 identity, so j3. All right, let's work out what that is. So minus lambda 3 times the identity matrix. Okay. That means I'm subtracting lambda 3 from every diagonal entry. Okay, so this is the same as the matrix lambda 3, lambda 3, lambda 3, all down the diagonal.
Right.
So what is the matrix I end up with for j3 minus lambda 3 identity? There's not much left.
Well, the lambda 3's all disappear, right?
Yep.
So and then you just end up with a 0, and then there's a 1, right? And then
Yeah, so that's it.
yeah.
So it's good there's not much there. So then we can take powers of that. And since most of the entries are 0, we can bet that there's going to be mostly zeros when we take powers of it. All right. So then j minus lambda 3 identity, or j3 lambda identity squared is going to be equal to this matrix squared.
Okay.
Okay. All right. Now, it'd be kind of tedious to work this out entry by entry. Although one thing is oh, hi.
Oh,
Hi, Kevin. Hi.
Thank
Thank you.
you.
Oh, you did. Hi. Yep.
Oh, sweet. I don't know.
Well,
My phone died, so I had to go
well,
over Teams.
What?
I had to go message over Teams, so I didn't know if she got it.
Oh,
I
well,
didn't know if it was a hot chocolate.
oh, I don't know yet.
Find out.
Okay.
I'm sure it'll be delicious.
Yep.
Yay.
Okay. All right. So if you were to work this out, it's almost entirely 0. You just get a 1 up there. Okay. So then if we go further, so that would be the square that we just got times j3 minus lambda I So then you would work that out, and I'll just cut to the chase here. It's big fat 0. Well, certainly all powers past that point will also be 0. Okay, so this is an example of what's called a Nil Potent Matrix. So any matrix that is non-zero, but becomes 0 once you raise it to a sufficiently high power, it's a nil potent matrix.
Nil potent.
Yeah. So in fact, any matrix that is strictly upper triangular like this one is, where like a diagonal is 0, or lower or strictly lower triangular, would be an example of a nil potent matrix. Because notice what happens here. Here's what we started with. Then the square, it's like we're taking this diagonal and we're chasing it out. Because it moved up here, and then we chased one more time and it's gone.
We did something like that in linear, didn't we?
Maybe.
I just remember pushing entries out.
That's for similar Gibbons rotations.
Yeah.
Yeah. So, yeah. So even though what we have here is an infinite sum, it's actually a finite sum because most of the terms are 0. So now that I know what all the powers of J3 minus lambda free identity are, I have expressions for them. Now I can work out what that is. Okay. Questions about any of this? All right. Now let's write out what this is in full. Okay. So, what we end up with is e to the lambda 3t multiplying everything, the factor of the sum. Then for first terms for k equals 0, well, that's 1, that's 1. This is identity, so we'll just have identity. It's the first term. So this is for k equals 0. Then we do k equals 1. So that'll be e to the lambda 3t again. Times t to the first over 1 factorial, so that's going to be t. Well, I'll just put the t up front. Times j3 minus lambda free identity to the first power. That's 1, 1, 0. So this is for k equal 1. Plus 1/2 t squared e to the lambda 3t times j3 minus lambda free identity to the second power. And that has nothing except that one entry in the upper right corner. And then that's it. There are no more terms because any of the powers of j3 minus lambda free identity will be 0. So then I just add all of these together, and sure enough, that's the matrix we got that describes the solution to our system of ODEs. So, and zeros down below. So what this tells us, now this is definitely not a proof, this is so non-rigorous, although I think perhaps more illuminating than a proper proof would be, that the solution of y prime is equal to a y is y of t is e to the a t y of 0 for any square matrix A, diagonalizable or not. So when it's diagonalizable, you can solve n ODEs independently and get a solution that way, because we know how to solve those. And we get to matrix exponential. If A is not diagonalizable, we use a Jordan form. It doesn't matter whether it's a 1 by 1 or larger Jordan block. What we get is still the exponential. What I've done here in this specific example could certainly be generalized into a proof that what you're showing is that for any Jordan block that would have the same form as this one, just a general size, that this is what you get for the exponential, because you only have a finite number of terms. And then you could show that the solution of a corresponding system of ODEs has that same form, because when we solve this system of ODEs, we solve for this one first, because independent of the others, then use that as a source term for the next one, the next one. Like you could show, like using an inductive argument, that that's the solution. So even though what I've done is shown you for a case of system of 3 ODEs that are described by a non-trivial Jordan block, how this was worked out, you could see how a proof would go. Yeah. No, I'm not going to give it as a homework problem.
Oh, okay.
Yeah.
I was wondering if you were leaning. It seems not like a fun one, but it makes sense, I guess.
Okay. All right. So in general, for first order systems, where you have a constant matrix and some source term. So if this is your system of ODEs, then your solution is e to the at y0 plus the integral 0 to t e to the a t minus s b of s ds. So we can just, so what we'll do going forward is take that solution formula for granted in working with certain particular systems of ODEs of interest. In particular, those systems of first order ODEs that are obtained from higher order ODEs that have been rewritten as first order systems. And some of those cases will lead to a diagonalizable matrix A and some will not. Okay. But what I want to do is, before making use of this solution formula, I wanted to at least, if not prove, I did not prove where it came from. Because I did prove this for a case of a single ODE, so where a matrix A is 1 by 1. And while I've not proven it for a case of a general square matrix, except for a case where it's diagonalizable, at least I've made it plausible that this formula is correct. But it makes sense that you'd have a common formula regardless of what type of matrix it was, regardless of whether it was diagonalizable. Okay. And what you can always do to prove that this is a solution is just all right, you're all going to hate me for this, but okay. So, well, I'm not going back on word. I will not make you prove this formula. But here's what I will do. So your next homework assignment is to verify this solution formula. And what I mean by that is take this y of t and substitute it into the ODE and show that everything really is equal, that the derivative of this with respect to time really is equal to a times this this expression plus b of t.
Okay, so we're taking y of t and plugging it into that
Yes.
y over there.
Yes,
Okay.
on both sides, show that everything really is equal.
Plug into. Okay.
Now, so something you can use to help with that is the fact that the derivative of e to the at is a e to the at.
Okay.
So that'll certainly help. Also, another key property of e to the at is that e to the a, when you plug in t equals 0, well, of course, e to the 0 is 1, so that would be the identity matrix. So those are the essential properties, really, that can be used to define the matrix exponential that will be helpful here. But what you also keep in mind is, for handling this part, when you take a derivative of this, fundamental theorem of calculus, you're taking the derivative of this with respect to t when t is a limit of integration.
Right.
So fundamental theorem of calculus explains how you take a derivative of that. And what I would recommend here is factor out e to the at, because you're allowed to pull out anything that doesn't depend on s.
Right.
So
there's like the first time where we always did that.
yeah.
Okay.
Yeah, so that'll make a differentiation easier. So I guess that's one way to prove that this is a solution. So I'm having you prove it, just not in a really god-awful way.
Okay.
And this really doesn't depend on, this has nothing to do with whether A is diagonalizable or not. Because all you're using, the only properties of the exponential you're using are these two. Okay. So are there any questions? Well, okay, well, about anything, whether it came from this problem or what else I did today, or the previous homework.
So this is just for a general e to the at, whereas what we verified earlier was dealing with the Jordan blocks.
Yeah, for a case where the matrix is not diagonalizable.
Right, so this is not necessarily to do with diagonalizable or
Right.
non-diagonalizable.
Yeah, but you're using this that holds regardless of what A is.
Okay.
And in fact, this you could show using the Taylor series expression for e to the at. But if you took that infinite sum and took its derivative with respect to t, and simplify as much as you can, you find, oh, it's equal to A times that. Using some summation shenanigans.
Will that be like necessary within?
No, I'm not having it, that's not part of the problem.
Oh, okay, I was
I'm
just
just saying
making
how,
sure.
yeah, I did consider that, but I don't want to keep adding to the problem.
Okay, no, that's fine, I'm just making
Yeah,
sure.
yeah, but that's how you would show it.
Where are you wanting us to do a previous homework?
Oh, sorry, what?
Like, what do you want us to do when we finish a homework?
Oh,
Because I forgot about the other one, honestly, I just.
oh, okay, yeah.
I mean, I need to probably check through it still, but.
I just realized that I didn't do anything to make it possible to submit for candidates like I usually do. You can just email it to me.
Okay.
Yeah.
I'll just do that.
Yeah. Okay. All right, so no questions about anything? Anything at all? For those of you on the coast?
I'm okay right now.
Well, just making sure.
Gotta let it soak in for a minute.
Okay. All righty. I hope that I am. I remember to take pictures of everything. I think I did. Okay. Sorry, I haven't gotten around to transcribing the last set of notes. Being away at a conference over the weekend, gotten away of things, but hopefully I can do all that soon. Okay, I guess we're wrapping up. Well, I guess it doesn't make any difference for 2/3 of you. On Thursday, I will be at the coast, at the Gulf Park campus. So we're all virtual.
Okay.
Yeah. All right. Okay, stop recording now.